So now we need to make a conclusion that makes a quantitative comparison between the physics theory and relationship from the experiment, including a consideration of uncertainties. This is all level 3. So let's have a look how to do that. So I've got my graph, including a full consideration of uncertainties with the error bars and the line of worst fit. I've got my information off there, and I've calculated the uncertainties in my gradient and y-intercept. Now, just having noticed one thing here, we haven't put any units on, so that's uncertainty in the gradient will be in seconds, because that's on the vertical axis, and the horizontal axis is meters to the square root meters. So let's use index notation for that. Now meters to the half, and we actually want a little fraction sign for that, 1/2. Now I've deliberately made a mistake here, okay, because it's meters to the half, or right, square root meters, but it's a gradient's always the vertical divided by the horizontal. So in fact it's to the minus 1/2, because it's seconds per square root meter. Right, and obviously the y-intercept, that's just plain old seconds. Right, anyway, moving on. So now we've got to write out our equation. It's always in y equals mx plus c form. Okay, so let's just think really carefully about this. So on my y-axis is t, on my gradient, my m value is 1.3, my x-axis is the, I'm going to put it times, and then the square root of d, and then take away 0.01. Now that's the level 2 version. Now we have to include our uncertainties. So the gradient, now I'm going to put this inside a bracket and you'll see why in a minute. Okay, the gradient is plus or minus that value we've just worked out through here, the uncertainty in the gradient. So it's plus or minus 0.3, 1.3 plus or minus 0.3. And the y-intercept, and 0.1 inside a bracket, just like I did before, and for exactly the same reasons. Bracket, and then I put my plus and minus, and it's 0.14. 0.14. So there's my equation, including a comparison of uncertainties. Right, now the theory equation is t equals 1.22 times the square root of d. Now let's have a careful think here. Are these the same thing? Well, in terms of the shape. Okay, let's just do the one step at a time. So both the theory equation and the experimental equation have a, and I like using the same font, so t is a function of square root d form. Oh. Okay, so they both have the same form of the equation. They both show t is a function of square root d. Okay, now 1.3, well, is it the same as 1.22? Now, let's think really carefully here. So let's consider the range in our gradient. So put a new equation on. Let's get some greater than or less than signs. So the smallest our gradient could be is 1.3, take away 0.3, and the biggest it could be is 1.3 plus 0.3. And we could just summarize that very quickly here. So the smallest it could be is 1.0, and the biggest it could be is 1.6. Right. Now, for ease, I can just copy that, pop that there, but we can do the same thing for the intercept. So the smallest our intercept could be is negative 0.01, take away 0.14, and the biggest it could be is negative 0.1 plus 0.14. And paste that there again. So that would be negative 0.15, the smallest it could be, and positive, to stress, 0.13. Let's put a space there. So there's the range I have for my y-intercept as well. Now, what does that say about the theory equation? Now, we already talked about the shape. It's a square root shape, and I've written this out already because my typing sucks. So our theory gradient is 1.22. That does fall within our experimental gradient range of 1.0 up to 1.6. So we've confirmed the theory gradient. And similarly for the intercept, and you'll notice I've put a plus 0 on here because it's just to make the point really, there's no intercept, and that 0 does fall within negative 0.15 and positive 0.13. So we've also confirmed the theoretical intercept. So as we've confirmed the shape and the gradient and the intercept, all the features of our equation, we have confirmed the theoretical relationship.